So I have tried to upload many of the videos. So I just posted the YouTube link as well. So you can look at them. If you are missing any lecture or if you are missing any section, you can basically refer to that video. So other than that, the last time we are basically discussing about state space concept. So we will quickly wrap the state space concept today, and we will do one numerical technique for calculating the dominant eigenvalue. So today what we will be seeing is some more discussion on state space concept and numerical computation of dominant eigenvalue. So we'll try to cover these two topics today. So what we saw in the state space concept, if we have we started with, I believe, the second order differential equation. So let's say if I have a differential equation which is given by x double dot as a x of t plus f of t. So what state space concept says that if you are given a specific x of 0 and x dot at 0. So let's say you are given the second order differential equation and we are given the initial conditions to solve this differential equation. So one way that we can solve is if it is a coupled system where A matrix is not diagonal, then we can basically, if A is not diagonal, then we can use modal decomposition technique to diagonalize it. So then we know that we can either have, we can write x as p of y if A is diagonalizable, or if A is defective, then we can write x as q of y. And I'm not going further into the discussion about what p and q are. Basically, we saw that p matrices is constructed of all the linearly independent eigenvectors of matrix A, and q is constructed out of the missing eigenvectors plus all the other linearly independent eigenvectors of the defective matrix A. So we can basically proceed, and if we substitute this variable in this equation, we can diagonalize it, or we can make it in a Jordan form, which helps us to decouple this system of equation and solve it. The other approach that we actually saw is we can convert this system, second order differential equation system, into first order differential equation. So reduce nth order differential equation into first order differential equation into a sequence of first order differential equation. And the way that we actually implemented is using state space concept. And what it basically says that we deal with some new variables, which we call as state variables, and the number of state variables will basically correspond to the initial conditions that are specified to solve the second order differential equation. So for any nth order differential equation, if you have to solve that, you need n initial values to get a solution. So here we have second order differential equation. So we got two initial conditions. Now, since we have two initial conditions, so we can basically start with two variables, state variables, which let's say we have u1, which corresponds to x, and u2 that corresponds to x of dot. So we have two variables, and using these two variables, you can convert this system of equation into set of first order differential equations. So one of that is simply u1 dot as u2. That is one equation. Another equation is, if you look at there, so it is u2 dot is equals to a u1 plus f. So these are the two equations that basically completely represent the system of system given by this expression. Let me know if it makes sense to you guys, or if you have any questions or concerns.
I follow you.
Professor, how did you get those two equations?
So for this, let's look at the second equation. So here what I did, instead of x double dot, so I replace it with u2. u2 is already x dot, which is time derivative of x. So if I basically replace it with u2 variable, then it will be u2 dot. That's how this equation is written, right? And x is u1, so a u1 plus f as it is, remaining as it is. You got it, what I'm saying for this equation?
Okay.
And the first equation is simply, I rewrote this this variable, choice of variable. So I know u2 is x dot, I'm a derivative of x. So x itself is basically another state variable, which is u1. So basically u1 dot is equals to u2.
Got it. Thank you.
Yeah.
Professor,
Yeah.
so
yeah.
So for an n order, we can only have n number of state variable.
Yeah, there will be n state variables for nth order differential equation. So at second order, we have got 2 state variables. Third order, we'll have 3 state variables. Nth order, we'll have n state variables. So
and then the derivative is only to the first derivative.
Every equation will be only first derivative. So the way you are basically constructing the system of equation is that all the independent state variables are appearing on the left hand side with only first derivative. That's it. There is no other derivative. So u1 dot, and all the right hand side will involve other expressions. So it will not involve the derivative on the right hand side. So you will basically see that it only has this expression on the right hand side only has the variables u1, u2, f, and so on and so forth.
Thank you.
Yeah, welcome. So if I write this in matrix form, I basically call that as u dot is equals to okay, so here now I'm assuming this is just one scalar, because at this point of time, you generally need to expand this. If this is not a constant, then basically you need to expand this and the matrix will not look like this. At this point, I'm assuming this A is just one scalar number here. So that will basically give me 0 plus 0 and f. Does it make sense to you guys?
Yeah.
Is everybody following?
Yes, Professor.
Yes.
Okay, great. So just give me a second. I'm just looking at the actual expression we had. Okay. So here, the only thing that I wanted to lay stress here, this A is a scalar quantity because X is basic, this X double dot, this X is just one scalar. So it is not any, it is a one dimensional vector. So A is a scalar. So that's how I can write it in a matrix form. So A is a scalar quantity. A is not a matrix here. A scalar. It can be a matrix, but at this point I'm considering it, assuming it is a scalar. That is my assumption. That will basically, that allows me to write it in this form. Okay, so with that said, this basically becomes u dot is equals to this whole matrix. Let's call that as B, U plus F. And the solution for this first order differential equation, ordinary differential equation, is given by u of time t is equals to e b time t 0 to integral 0 to t f of t e b t minus tau d tau. So that is the generic expression for any first order differential equation, which is a linear. So this is a linear.
So is it f of t or f of tau?
F of tau, yeah, you're right. Thank you. Linear first order ODE. Yeah, I'm just making sure the expressions I'm using are correct. Okay. So this is what we stopped in the last lecture. We actually stopped at this expression, and this expression basically involves the matrix exponential. We said that this is what we call as matrix exponential. And the way that you can calculate matrix exponential is you can use the eigenvalues of B and you can calculate what this term will look like. So
Professor, what's the difference between t and tau?
T is the time, representing time, and tau represents the dummy variable for this integral, performing this integral. So tau can be x, y, z, anything, and it has basically the integration is with respect to tau, not with respect to t. So t in this integral is t is constant. You have to assume t is constant. Once you get this integral evolved, and this integral itself will be function of time.
So tau is just a dummy variable and it can be anything?
Yeah, tau is just a dummy integration variable.
Oh, okay, for sure.
A dummy integration variable. Okay.
Got it.
Great. So now what we are saying that in this expression, everything makes sense. I mean, we can do the integrals if we know that function, what the function is. But before we actually perform the integral, we actually need to know what this expression means. What is this matrix exponential? So far, you know, a exponential raised to power a scalar quantity or scalar number, but what if it is a matrix? So what if B is a matrix, then the expansion of exponential series remains the same. So basically, if I have, let's say, EBT as, if I have to expand that, so in matrix terms, it will be I plus B t plus b squared t squared by 2 factorial plus so on, and it will be an infinite series where B is a matrix, I is a matrix. So the size of the matrix depends on the size of the matrix B. So in this case, our B is basically a matrix of 2 by 2. So that means this is 2 by 2, 2 cross 2. So identity matrix is again 2 cross 2, B is 2 cross 2, and so on and so forth. Is everybody following it so far?
Yeah.
Yes.
Yeah, so it is, B is not a scalar number, and this is an identity matrix. It is basically 2 cross 2. Everything, all this sum, infinite series sum, is a 2 cross 2. Now, there are easy ways to find out this matrix exponential. So if B is diagonalizable, or if B is diagonalizable, then matrix exponential E can be written as P E D T P inverse, where again, you know what the P basically means. P is, and what D matrix means. So D matrix is consisting of all the eigenvalues of this matrix B in diagonal form. So since it is 2 by 2, I'm just considering it as 2 by 2. Okay. So that is D matrix, and P, you know that this is constructed by eigenvector corresponding to lambda 1 and eigenvector corresponding to lambda 2. Again, it will be a 2 by 2 matrix. Okay. And EDT, now again, I replace this E raised to power matrix B times T as E raised to power D times T. Now again, I'm replacing one matrix exponential with another matrix exponential, but the advantage of using this is that I can write this as E lambda 1t 0 0 E lambda 2t. So in essence, exponential matrix exponential will become P times, which is 2 cross 2 times E lambda 1t 0 0 E lambda 2t, and P inverse, which is 2 by 2. Let me know if you guys are following it so far.
Yes, yes.
Everybody is following it, or everybody is
Yeah.
with me in the
just writing
same
it down.
on the same page? Sorry.
Oh, sorry. I was just writing it down. If you could give me like 30 seconds.
Sure.
Okay. Thank you.
Yeah, welcome. So now it becomes easier now if you actually look at this. It is just like if you know this is just a matrix consisting of the eigenvectors arranged in a column format, and the matrix exponential. If B is a matrix, 2 by 2 matrix, can be any generic matrix. It need not be just zeros, ones, it is not a diagonal matrix, as you can see itself. So if you find the eigenvalues of this, you can then represent matrix exponential of BT as in this form. And then when you use this expression in this, then you know exactly how to integrate it. So it's just like, you know how to integrate the individual diagonal terms and so on and so forth. So that is how matrix exponential is computed if B is diagonalizable. B is diagonalizable means B can be written in this form, or I'm sorry, B is diagonalizable means it has got eigenvalues that leads to independent eigenvectors, and that causes the matrix B to be written as a diagonal form. So if B is defective, as we know that if there are some repeated eigenvalues, or if there are no eigenvectors which are linearly independent, we need to use the equation of missing eigenvector. Then in that case, let me use a separate sheet. So if B is defective, in that case, matrix exponential is written as Q E JT times Q inverse, where J is the Jordan matrix form, and Jordan J is basically a Jordan matrix form. And for example, we actually saw in the very first example that we did, we saw that there are 3 eigenvalues. And once I did that, yeah, say some question, sorry. Karthik.
Oh, whoops, never mind.
Okay, so this is a Jordan block form or Jordan matrix, and in that case, we can represent this as 6, 6, 8, 0, 0, 0, 0, 0, 0 plus 0, 1, 0, 0, 0, 0, 0, 0, 0. So we can represent J as D plus delta, where D is a diagonal matrix consisting of the eigenvalues that you are seeing here in the same thing. And there is one extra term that is getting added extra, and we call this as delta matrix. So again, EJT, so how to compute EJT? EJT is basically going to be E D plus delta T, that is E D T times E delta T. E dt, we already know how you have to write it. And E delta T is given by the same exponential series. where this is again delta is going to be a 3 cross 3 matrix because our J was 3 by 3 matrix. This is just an example. Delta square T square by 2 factorial and so on. And the reason that it is not going to be an infinite series, but it is going to end at Tm minus 1 by m minus 1 factorial, because you will find that this matrix when is multiplying, when I say delta square means this matrix is being multiplied by itself. So that is delta square. So when you multiply this matrix with itself, there will be a time when you will have delta m will be 0 for this specific type of Jordan form. So if you have a MATLAB, or can you quickly find out what delta square would be? Delta square basically means this matrix is multiplied by this matrix itself.
Is it 1, Professor?
So this multiplied by this is what? How much you said?
Is it 1?
I'm not, I don't know, but if you are getting from the MATLAB, let's say that's 1. Now you multiply it again thrice. So delta Q, what is delta Q? I mean, this matrix multiplied 3 times. Again, when you multiply this with itself, you are not going to get 1 because this is a 3 by 3 matrix. So when you get delta cross delta, so delta square is delta times delta, which is basically this matrix, a 3 by 3 matrix times 3 by 3 matrix. So that's why I'm asking you to use some, quickly use MATLAB. Well, let's do it actually. I can do it easily here. So when you multiply this, this will be 0, 0, 0, 0, 0. It will be all zeros. 3 cross 3. So you will find that this, as I was saying, delta m raised to 0. So there, depending on the size of the delta and what that form looks like, there will be a time when you this matrix multiplied by itself m number of times will be 0. So this will not be an infinite series, but it will be having some finite terms. And for this specific application or example, what we are seeing that it stops at this number itself. You don't have any delta square, anything, because if delta square is 0 matrix, then delta cube, delta 4, everything will be 0, right? Delta cube will be delta square times delta, and it will be again 0. 0, 3 cross 3. It's not just scalar number, it's just 3 cross 3 matrix. Similarly, delta 4 and so on, everything will be 0. So we don't need to take all the extra terms in the infinite series. And what you actually will end up is 1 0 0 0 1 0 0 0 1, and here you have just t. I mean, this is multiplied. So let me know if you are getting what I'm doing here.
Yes, Professor.
So I mean, I'm giving you some few minutes just to make sure that you understand what we are doing. So I'm just showing you how to compute matrix exponential E raised to power the matrix B times T. So T is just a variable, so you don't need to worry about that. So we are worried about how to compute matrix exponential. If matrix is diagonalizable, then it only consists of diagonal terms, and we know it only consists of this specific matrix. That's it. We don't need to worry about anything else. But if it is a defective matrix, then we will basically get a Jordan matrix form as we have seen. And Jordan matrix basically will have this form where you have all the eigenvalues in the diagonal elements. And I mean, all the diagonal elements will be eigenvalues, and there will be one Jordan block as for the repeated eigenvalues. So we can decompose this matrix in T plus delta diagonal terms plus delta matrix. And when we compute the matrix exponential, we know to compute the matrix exponential for diagonal matrix, which is this. For this term, this matrix, I am to unfortunately use the series, but the nature of this specific matrix will ensure that at certain m is a positive number. It can be 2, it can be 3, it can be 4, it can be 5. This is basically going to be zeros. So 0 of specific size, 3 by 3 for our case. And we saw that for this specific example, delta square comes out to be 0 itself. So that means we only need to take I plus delta t term. And that's what I did here. I just use identity matrix and add delta times t. Delta matrix is this matrix times t means 0, t, 0, 0, 0, 0, 0, 0, 0. That gets added to the identity matrix and that becomes this matrix. Yeah, everybody is with me? And
Yeah.
to multiply these two matrices, you will end up with this E lambda 1t, t times E lambda 1t, 0, 0, E lambda 2t, 0, 0, 0, E lambda 3t. So essentially you only have this extra term that is coming because of the Jordan form. Are you guys getting what I'm trying to do?
Yeah.
Yeah.
So now you exactly know this specific, what this specific matrix exponential will look like, and you can take this matrix and put it in that expression to compute the integrals as required. So that will basically be substituted in this matrix. You can compute the integral. You can replace t with t minus tau, and you can compute the integral. Okay. Let me know any questions, guys. And take few seconds, couple of seconds.
So regarding the integral, how do we compute the integral when there's matrix?
So you compute element by element. So you compute for each element, you compute the integral separately.
Oh, okay.
Yeah. So if the integral has a matrix, so integral gets inside the matrix for each element. So you're going to integrate element by element. Any questions, guys?
That zero starting point for the integral, is it like, is that part of the procedure, or will that number?
Sorry, come again, please.
That zero, like the starting integration point, the zero to t, like, is that zero like coming from something, or? Yeah.
Yeah, 0 is coming from the solution of first order differential equation. If you actually solve this, you will actually find that you will end up with this integral starting with this lower limit as 0 and upper limit as specified variable t. So it is actually coming from the initial condition. So when you solve this first order differential equation, you need one initial condition because you have first order differential equation. So that initial condition is getting manifested in this lower limit of the integral as 0. Do you see what I'm saying? If you look at second order differential equation, I told you that whatever the order of differential equation is, you need as many initial conditions. So you have second order differential equation, you need 2 initial conditions. Here you have first order differential equation, you need 1 initial condition, right? And that is basically manifested in this specific lower limit of the integral as 0.
Can you please go back to the previous sheet?
Previous sheet, sure.
Thank you.
Yeah, welcome. Any questions, guys? So let me just recap what we were doing. So when we started the discussion on the eigenvalues, we basically saw how to compute the eigenvalues, how to diagonalize the matrices, how to compute the eigenvectors. And that's what we actually saw. So we focused our attention on this specific decomposition. Can we diagonalize it, or can we make, if it is a defective, can we find a Q matrix? So that's what our attention was. So that's what we focusing on, finding the eigenvalues. But let's say once the eigenvalues are obtained and we know how to do that, then we use them for the application of solving the differential equations. And the differential equations, we know that these are not just any arbitrary expressions, but they are coming from the physics of the problem. So if you have a dynamical system that has some physics, so X represents some state variables representing some, whether it represents displacement, whether it represents the temperature distribution, whether it represents the particle displacement. So it can be any physical parameter. And this specific expression represents the physics of physical formulation of that specific system. So if we have to solve and we have to understand the dynamics of that system, how the parameters are changing with respect to time, then we can solve them not very easily using our standard methods that we have learned in 501, but we can use eigenvalue concept to decompose or diagonalize the matrix, or basically make it in Jordan canonical form and solve it independently, basically to decouple the system of equations and solve them. And also, if it is not a second order differential equation, if it is some higher order differential equation, we can decompose into a first set of first order differential equations in state space variables. And we know how to find the solution for that state space variable using these expressions. And these are just thereafter, which we discussed, is how to compute matrix exponentials. So that's what the discussion was. So if there are no other questions, we can move ahead with the other topic. Otherwise, let me know if you have any questions.
Quick question, Professor, for that
Yes.
equation, for U of t, the integral equation.
Yeah.
So the first portion will be a matrix, and then inside the integral will be a matrix. So U of t will end up being a matrix, right?
Yes, U will be 2 by 2 matrix. Again, it will be a 2 by 2 and it will be 2 by 2 as well.
Okay, cool. Thank you.
Yeah. Okay, any other questions, guys? So if not, that completes the discussion on the state space concept. I will specify a specific homework. I will actually prepare a specific homework problem for you so that you get a practice on decomposing or reducing the higher order differential equation into linear first order differential equations using state space variables. That will give you some experience of working on these problems. So if there are no other further questions, we will actually go back to the second concept that we need to cover, which is how to numerically compute the eigenvalue. And here we are going to work with the dominant eigenvalue. So far, what we have seen is what we were doing is for computing the eigenvalues, we were basically solving this system of equation to compute the eigenvalues, right? Eigenvalues of matrix A, where A x k is equals to lambda k x k. So this is basically, we are trying to find the eigenvalues by solving the determinant, by basically making this determinant of this system equals to 0. That gives us a characteristic polynomial. Polynomial of degree n. And then you can solve the roots of that polynomial. You will get n roots, and those n roots basically corresponds to the eigenvalues of matrix A. Everybody is following it, or so far we are on the same page?
Yes, Professor.
Yeah?
Yeah.
So what we are doing is now, instead of actually solving this matrix, we are, let's say, we are interested in only one eigenvalue, which is the dominant eigenvalue. So what I mean here is that let's this system of this matrix A let's say it is an n by n system. So it has got n eigenvalues, and let's say they are arranged like this. So if I take the absolute value of this eigenvalue, absolute value of these eigenvalues, then they can be arranged in this ordered format where lambda1 is the maximum of all the other eigenvalues. So if I am interested to know only this specific eigenvalue, why I would be interested to only know this and not others? Because this is the eigenvalue which represents and which is called the spectral radius of matrix A, dominant eigenvalue. It is also known as rho of A or spectral radius of matrix A. And for any linear systems which are iterative systems, for example, let's say, if you remember our Gauss-Seidel iteration and Jacobi's iteration technique, we were using some form of, so we were basically using AX equals B, and A is basically decomposed as Q minus P X equals B. And what we were doing is that we are then representing Q inverse P XK plus Q inverse B. So we were using some iterative technique to solve our linear system of equations. Do you remember, guys, the discussion we are having?
Yes.
Is everybody following what we are doing here? So iterative method for solution of linear system of equations. And we saw that if A matrix is diagonal plus L plus U, and Q is your diagonal matrix, and P is minus L plus U, which is your Jacobi's technique, Jacobi's iterative technique. And if Q is D plus L and P is negative of U, that was Gauss-Seidel iterative technique. So the big questions always that comes is, in this iterative technique, we start with an arbitrary guess. So we start with x0, an arbitrary guess, and we keep on doing this iterative solution till we actually stop at the point where the residual of xk plus 1 minus xk norm is less than epsilon. So start with arbitrary guess of x0 and continue till we actually reach this condition. Now, the bigger questions for any iterative technique is, how can we guarantee that for any arbitrary x0 or starting point, this system of equation is going to converge? And to answer that, there are mathematical proofs which actually tells that for any iterative technique, this will converge if and only if the dominant eigenvalue, the spectral radius of this matrix, so rho of Q inverse P, is less than 1. And this is a spectral radius, and spectral radius is basically means dominant eigenvalue of this matrix system. Dominant eigenvalue, or the eigenvalue of this matrix, combined matrix, which is maximum in the absolute terms. So dominant eigenvalue of this matrix is less than 1. Then only we can guarantee that this iterative solution or iterative technique is going to converge. So there are many many other instances where there is a need for dominant eigenvalue. For example, if you work with vibrations and natural frequencies, then the first eigenvalue, the first frequency is basically the first mode or the natural frequencies, and thereafter the other eigenvalues or other following after first eigenvalue. Basically, this is a fundamental mode, and thereafter you have second harmonic, third harmonic if they represent the eigenvalues or they represent natural frequencies. So your fundamental mode, the first mode is always the most important one. Then thereafter you have second harmonics, third harmonics, and other terms that actually come after that. But always this is the one which is very significant to determine. And if you look at this specific polynomial of degree n, you cannot find individual eigenvalues. You have to solve the whole polynomial to find all the roots. There is no way that you can just find one root, and even if you can find one root, you are not sure whether you are finding this one or this one or this one. You don't know. You are not sure about that. Are you seeing what I'm saying here?
Yes.
Other guys, I mean, other students in the class, are you able to follow what I'm trying to explain?
Sorry, could you repeat that last portion once more?
So which one? From here or from here? Sorry, which portion you want me to go again?
When you're regarding to the dominant eigenvalue being less than 1.
Yeah, so what I was saying that if the dominant eigenvalue is less than 1, then this system of equation or this iterative technique will converge. Iterative solution will converge. Otherwise, it will not. You cannot guarantee it to converge. When I say converge, basically it means you can start with any arbitrary x0 starting point, and you can keep on marching in time or marching in the iteration numbers. And eventually what happens that after a certain number of iterations, let's say x11 or x12 or maybe x21, you'll find that x21 minus x20, the current iteration minus the previous iteration, there is not much difference in the estimation. So you know exactly where you need to stop, at what point you need to stop. But this stopping criteria can only be met if the system is converging, and the guarantee, I mean the condition that will guarantee that it will converge is the dominant eigenvalue has to be less than 1.
Okay, yeah, I was just concerned about the initial guess, because if I recall correctly in the previous homeworks, there was a problem where, or for the one we just turned in, that your initial guess mattered.
Yes.
And here it's not necessarily the case. It's just because it's dependent on the dominant eigen.
Yes, if your dominant eigenvalue is less than 1. If your dominant eigenvalue is not less than 1, then you cannot guarantee that it is going to converge. Then your system will depend on the starting guess. But what you are referring to in the homework is different thing. It's basically saying that for different starting guess, you are getting different solutions.
Okay, I see.
And this condition is saying that you will get some solution for any arbitrary guess if you have the dominant eigenvalue less than 1. If it is not less than 1, then even whatever the arbitrary value you take, you will never be able to converge. Basically, that means they are not getting any solution at all. Does it make?
Yeah, that makes sense.
So this is saying, this condition is saying that there will be a solution. Eventually, you will reach the solution. And whether that solution is solution number 1 or number 2, I don't know. But it will eventually reach to a solution. So that is the condition to satisfy or to guarantee that. Okay.
Yeah, thank you.
Okay, so then I was saying that using the characteristic polynomial, now the only method we know how to find the eigenvalues is to solve the roots of this characteristic polynomial of degree n. There is no other method we know. So what we are going to discuss next is how can we find the dominant eigenvalue. So to do that, I'm just writing some few steps of the algorithm we call as power method. And okay, so the topic is basically getting covered from chapter number 15. So in case you guys will be wondering where is it in the textbook, chapter number 15 talks about the numerical methods to compute the eigenvalue. So we may not get the chance to go through all the specific numerical methods, but I'm going to pick some few important concepts or techniques for computing the numerically computing the eigenvalues. So what we are doing is power method. And what this method says that let yk plus 1 is given by, is used as a of yk. And I'm just thinking a bit here. Just give me a second. Yk plus 1 is ayk. And compute mu k as yk transpose a yk divided by yk transpose yk. Then this is number one, step number one, number two, number three, compute then residual r as mu k yk minus a yk. Okay, and then fourth, if norm of r is less than epsilon or k is greater than equals to m, stop, else continue to step number one. So I will explain you these steps in a second. I am just writing this algorithm and will explain you what we are doing here. So we start with k equals 0. And epsilon is, again, you can approximate as 10 raised to the minus 6. And m is total number of iterations. So I just give you the algorithm without giving you the proof. So let me actually give you the, let me derive that why or how this algorithm basically computes the dominant eigenvalue. Dominant eigenvalue is given by the mu k, this number. So let me actually derive what we are doing here. So what we are doing here is that we are trying to take or start with any non-zero vector, y vector. So we got that as, we call that as y0. Okay, any non-zero y vector which has a dimension n cross 1, depending on if your matrix is size n cross n, then I will start with any non-zero vector which is given by y0 n cross 1, any non-zero vector. And then I compute using this iterative relationship where I'm just multiplying basically y1 is equals to a times y0, y2 is equals to a times ay1, y3 is ay2, and so on. I'm just basically getting specific y's at different iteration as a matrix A multiplied by the y value of the previous iteration step. Everybody is with me so far? And forget about this for a time being. I will come to this explanation of these steps. But what I'm right now doing is just trying to construct what this algorithm is doing. Let me know if you guys are with me so far.
Yes.
Yeah, I follow you.
Yeah. So okay, one thing that I'm missing here is yk plus 1 is equals to yk plus 1 divided by norm of yk plus 1. Okay, so here yk plus 1 is equals to yk plus 1 divided by norm of yk plus 1. So what it is doing, it is basically constructing, normalizing the vector a or vector yk plus 1. So first it is basically multiplying with yk plus 1 is a times yk, and once you are computing it, then you are normalizing the magnitudes of this vector using this relationship, where you are basically going to divide this vector by its norm, and you know how to compute the norm, right? Yes, so far the norm is just L2 norm. It is basically, if you remember excuse me, if you remember the norm of a vector, it is given by square root of the term square of the individual elements of the vector. So this is just L2 norm. You guys remember what we are doing here?
Yes.
Yeah. So this is just a normalization. You need to do the normalization at every step of the increment. And this is how these matrices are, or these vectors are constructed. Now, if you keep on doing that for a large number of times, what happens after certain number of time, what will happen that this vector is, or can be approximated as lambda 1 raised to the power n summation C1, not summation, C1 X1, or yeah, X1. So what we are doing, if you keep on multiplying this vector with itself, I mean, you start with any non-zero vector, it is an arbitrary vector, and you keep on multiplying with matrix A, keep on multiplying with matrix A, for y2 multiply with A, and then again for y3 multiply again with A. And if you keep on doing that, what you will see that this y, after a certain number of multiplication, this will be just the first eigenvalue, dominant eigenvalue, raised to the power n, the power, how many number of times you are multiplying it, times a constant. It's just a one constant. And this is your eigenvector corresponding to lambda 1. Are you guys getting what I'm trying to say?
Yes.
Yeah. So lambda again is just one constant, and c is another constant. So if these are two constant, and this is basically another constant. So what this yn corresponds to is nothing but, if you remember, we were discussing that an eigenvector represents a direction. So this is an eigenvector corresponding to lambda 1, and these are just constants. So constant multiplied by that vector will again be the same vector. I will basically be the same, will point to the same direction, but multiplied with that one constant. Are you getting what I'm trying to say here, guys?
Yes.
So if x1 is an eigenvector corresponding to lambda 1, then what will be y1? Y1 again will be the same eigenvector corresponding to lambda 1 multiplied with a constant. Is it making sense, guys? Now I actually skipped few steps here to show that why we are getting this as lambda 1. I mean, I left this as an exercise for you. I mean, this is there in the this derivation is there in the textbook. So I skipped that few steps here to show that why I'm going to get this y vector as lambda 1, the dominant eigenvalue, raised to the power n, which is how many times you are multiplying this vector by itself, times a constant c1 times its eigenvector. So assuming that after doing all those steps, you reach this point. From here onwards, do you follow what I'm trying to say? That yn is basically nothing but the same corresponding to the same eigenvector corresponding to lambda 1. Are you guys with me?
Yeah, Professor, just to clarify, what's the symbol in between lambda 1 raised to the m?
Nothing, I just crossed it actually. There's nothing.
Oh, okay.
So let me write, this is nothing, it is just lambda 1 n c1 x1. There is nothing, this is basically nothing. Okay. Any questions, guys, so far? Are you guys following it? Top of page. Yeah.
I was going to point out someone wanted the page to scroll up.
Which one? This one?
Yeah, I think so.
I will come to these steps in a second. I will come to these steps in a second. I'm just trying to explain why I wrote these steps. So that's what I'm trying to explain here. So once I finish this, I will go back to those steps. Just give me a few seconds.
All right, thank you, Professor.
You guys are following what I'm trying to say here? That if you keep on multiplying, if you start with any non-zero y vector and you keep on multiplying with matrix A times A times A times A times A times A times A, you eventually what you will end up with this vector, what you will get will be the same as a dominant eigenvector. After n multiplications. Okay. Now why I got this? There are few steps. I did not do that in just to skip some of the algebra there, but eventually you will end up with that. And there is proof for that. I'm just not using those specific steps here. I'm just not using that. So eventually I reach that result, and that result says that if you keep on multiplying an arbitrary eigenvector with itself, with the matrix, keeps on multiplying with its matrix, eventually after sufficient large number of multiplications or a large number of n, you will end up with a vector which is going to point in the same direction as your dominant eigenvector, which is your x1. So assuming that you guys follow this, so what it says that ax1 is equal to lambda 1 x1, because x1 is an eigenvector corresponding to lambda 1. So this is basically satisfying this equation. Now if I multiply with x transpose, x1 transpose, x1 is, remember, lambda 1 is the dominant eigenvalue. And x1 is the eigenvector corresponding to lambda 1. And we have not found lambda 1 yet, and we have not found x1 yet. We are just using symbolic terms, but when we multiply y, take arbitrary y0 and multiply with itself after certain number of steps, what we get, that will actually be your x1. That is basically going to resemble the same direction as your eigenvector given by x1. Eigenvector corresponding to lambda 1. So if I multiply this with x1 transpose on both sides, then what I get, lambda 1 is given by x1 transpose a x1 divided by x1 transpose x1. So you can find lambda 1 using this equation. Let me know if it makes sense to you. Are you guys following it? I'd appreciate some response, guys.
Yeah, Professor, what's the difference between x1 on the left side and x1 on the right side? And yeah, up there. Yeah.
These are same. Remember, you for eigenvalue, you actually solve this equation ax k is equals to lambda k x k.
So why don't we just cross them out and say lambda 1 equal A? I'm confused.
So that's now how the matrices work. So lambda is a scalar number and A is a matrix. If I just,
Oh, okay, okay.
yeah, you
Yeah,
see,
that makes sense.
okay.
Thank you.
Are you guys following it?
Yeah.
Yes.
Yes.
Great, thank you. So this is how you-
What's the point of multiplying by x1 transverse?
so when we multiplied this with x transpose, this will become one number, scalar number. Right now, this is a vector. I cannot take this vector and put it in a denominator. So if I multiply this vector with x transpose on pre-multiply with x transpose, then it becomes one number. So let's say x1 is a 3 cross 1 vector. So let's say I'm just using
Okay, I got it. I got it.
okay, got it. Thank you.
Thank
So
you.
x transpose x basically becomes one number. Now, if this is a number, just one number, then you can take it in the denominator. Otherwise, you cannot take it in the denominator. So that is the reason we multiply with x transpose on both sides. And once we multiply that, we basically end up with this number, and that will be your lambda 1. Now here in this whole, when we start with this, I asked you to just forget about these steps at this point of time. I asked you to focus on these steps. So I start with a non-zero y vector, and it can be any vector. I mean, it can be 1, 0, 0, 1, 0, 1, 1, 0, -1, whatever that is, number of your choice. Start with that vector and keep on multiplying with A. But when you are multiplying it, we always remember that you are going to normalize it as well, so that you are not just multiplying it, you are actually also normalizing it. So when you keep on doing multiplication with A and A and A, after multiplying with A times A times A times AY, what you will end up with eventually, this vector will be your x1 vector, will eventually reach the point when y1, or this will resemble your x1 vector. That means you have got the x1 vector using these multiplication. Once you got this x1, now I need to find lambda 1. How can I find lambda 1? I use these expressions and I can use lambda 1. Let me know if you follow this much, guys.
Professor, I got a question. Is y subscript n dependent on your iteration cap k that you enter in the beginning of?
Yeah.
Okay.
So at this point, this is undefined. I not defined what n is going to be. I just leave it. I leave it any large number n. That's it.
I see.
Yeah. So once you have reached a specific large number, what that large number is, I have not specified to you. But let's say you have gone to a large number. You eventually your yn becomes equals to your x1, which is your eigenvector. Dominant eigenvector corresponding to lambda 1. And then using this expression, you can find what lambda 1 is. If you understand this much, then we actually we combine this specific line of thinking into this algorithm. What the algorithm says that you start with k is equals to 0 tolerance level and total number of iterations, and you start with an arbitrary guess. Start with y0, arbitrary choice of vector, arbitrary. So you say y1 is equals to a times y0, and then you normalize it, and then you compute this number, and that is your eigenvalue, lambda 1. Basically, that's what we are trying to find out, y transpose ay divided by y transpose y, assuming that in the first iteration itself, you have found the eigenvector, the dominant eigenvector. So if you assume that and you find the eigenvalue, if you remember that what we have done, lambda 1 is x transpose ax divided by x transpose x. So in the first iteration itself, if I found my eigenvalue, that's what I'm calling it as mu k. Now, if mu k is my eigenvalue, I found this residual, and this will be 0 if mu k is really the eigenvalue. Then this is basically coming from this step. So here, lambda k, if you look at this step, lambda k xk minus a xk will be equals to 0, isn't it? Right? If I take this on the right hand side, it basically becomes this equation, right? Yeah. So that is what I'm doing here. So if mu k is really your eigenvalue, you have found it from the first iteration itself, then mu k times yk, that is lambda k times xk. The mu k is the eigenvalue for kth iteration times the eigenvector for the kth iteration minus a times yk minus a times xk. So a times yk, this will be equals to 0 if I have found mu k as my eigenvalue. But it will not be the case. That means the norm of this vector will not be less than epsilon tolerance level. I have to keep on doing this multiplication back again. And you have to do those iterations repetitively till the point you reach when this residual vector becomes equals to 0 or less than a tolerance level. When it becomes less than tolerance level, I will stop, or my iterations level actually reach the total number of iterations, I will stop. Else I will keep on doing step number 1. That is, I'm always for step number 1, again, if I go back, I multiply again with a. So I continue to step 1 with k equals k plus 1. Then I change the increment and I then multiply the previous yk with a again, redo those steps, see if my residual is less than epsilon or not. If not, again I multiply with a, redo all these steps, see whether the residual is less than epsilon. If not, again multiply with a, and then eventually after certain number of iterations, after large number of multiplications by itself, you will find this residual will becomes less than epsilon. And that means you have find the dominant eigenvalue lambda 1. That is what we were targeting from the beginning. Let me know if you guys are following it or with me on this.
I follow.
Any questions, guys? So if not, then I will stop at this point of time, but at the same time, I will ask you guys to look at the textbook and see what are those missing steps here that leads me to yn becomes equals to lambda 1, because that will make you understand more and appreciate the technique and how this technique is working. But if you understand that what I have said, then the algorithm and these steps should be making sense to you at this point.